Good afternoon. Okay, so I hope you are well. Backbenchers, you're making noise. All right, so I hope you guys are well and you're coping with the heat. 1 minute it's cold, the other time it's very extreme. But you're lucky. I mean, we have power within NRDC. Okay, so last time we met, we were talking about submerged surfaces, and we discussed the importance of knowing the pressure at any point we are considering, but then it doesn't just end there. We are also interested in exactly where it is. So with that topic, that's all it ends. But I remember us doing just one section that involved us dealing with a vertically placed plane, not so? Yes. There was one that was on an incline, on an angle, 45 degrees. I hope you found time to do that because the principle is just the same. And I mentioned that, look, just go try this on your own individually, and then you meet as a group, you do the work. If you make it, as in you graduate all the way to third year, we will, it's basically the same sort of approach that I have. And I picked this when I was at UNZA. UNZA, those guys don't teach. They'll show up with the material and the mod, just dump it in your face, and they'll just be telling, okay, we are looking around this topic. So the bulk of the time that I was there, it involved us studying, us researching on our own. So you won't have everything handed to you on a silver platter. So some things, zambo punzi sako vina ngutasi yako, knowing that you guys are becoming researchers, yeah? I need to start paying attention to people's faces. I think I've said this before. Or you guys just change every time we meet. I can point at 10 people just from what I can see, not even at the back, no, just here. That I'm thinking, we have never met before. Huh? What's up with the coughing? Huh? I thought it's warm now. It's the cancel class, eh? Okay, so let's talk about the hydrodynamics. So this is an interesting topic. If you have found time to look at past papers and then they are asking you to can we keep quiet? Oh, it's outside. All right, so let's talk about the general concepts. Okay. What do you understand by hydrodynamics? What comes to your mind when you put those two words together? Hydrodynamics. Dynamics, hydrodynamics. Anybody? Yes, sir. Fluid motions in the fluids and the forces that are in it. Okay, anybody else? Hydrodynamics, what comes to mind when you hear of a hydrodynamic fluid? Yes, madam.
I think we're looking at a fluid that is in motion.
Fluid that is in motion. Yeah. So you're both right. It's the bulk of what we've done so far. The biggest assumption has been that we have this water which is stagnant, right? It's still, it's static. It's not really moving. That's everything we've done so far. It's only now that we're jumping over to the other section where we are looking at what happens when fluid is moving, okay? If you've looked at the past papers, you find a question that looks like, it's called branches, eh? Have you ever seen this before? Yes. And then at every point of that pipe that is supplying and then it branches off, we are interested in the discharge, we are interested in the velocity, we are also interested in, well, many other parameters can come from this. Velocity, discharge, of course, we are also given diameter, all right, of that fluid. So how do you relate the water coming from this end and us reducing or forming two pipes, breaking away from one major pipe? So if my discharge is so much from one major pipe, I need to decide how much will be going this side. I need to decide what is going that side. And all of these dynamics need to be considered, and they can be calculated. So we don't just guess, say water is coming from here, but then this other household needs so much, and then let me just go pick up a pipe. You can literally calculate how much water you want to be going to one area. And the size of a pipe that you get will influence the rate at which you'll be receiving that water. Are we together? So that topic is this one, and you should be able to solve something like this. And there's usually a table, not so. Yeah. I told you NRDC passing exams here is not really rocket science, unless you just want to make it that way, because there are always past papers leading to your exams. So to reach an exam and still get shocked at an example or a question, it just means that you weren't studying. In short, we recycle a lot of material. We may change one or two things. Yeah? Okay, so hydrodynamics. Let's talk about the general concepts, okay, that are going to be found in this. Okay, so I'm going to do a lot of dictating today. I'm hoping the next time we meet, we'll actually do an example, and then we're done with this topic. Do you know Mr. Manza? Yes. Did I tell you that he taught me? The HOD. The HOD, water engineering. Yeah, he taught me. Yeah. This course, actually, he taught me. Or like his staff? No, not really. Yeah, no, he's a genius, that one. But when you get to know him and he considers you as his equal, he treats you with more respect. So for usually first year, second years, when you reach third year, you see him starting to chat with you guys, all right? But anyway, the reason why I mentioned his name is, he would always say, whenever he would say that, look, This topic, I know it's got about 50 pages, but we should be done in the next 2 days. And then we'd also react the same way you guys are reacting. And then he would just say that, look, we are moving at the speed of light. And then we'll continue, right? Okay. So hydrostatics, so I'm dictating. Hydrostatics involves only a few variables. Hydrostatics involves only a few variables. Hydrostatics involves only a few variables. And these are the variables, and we've looked at them before. This looks like rho to me. And then we've got a gravity here. And then we've got an H, which is usually head, not so. So I said hydrostatics involves only a few variables. And those are the variables that I've written there. And so the equations developed are relatively simple. And so the equations developed are relatively simple. And so the equations developed are relatively simple. And experiment and theory closely agree. And experiment and theory closely agree. And experiment and theory closely agree. Okay, so we continue. So again, be writing, put them in bullet forms, huh? Because I'm just extracting the most punchy points. Have them as points. If you have them, it's easier to just go through whenever you've got the time. The study of fluids in motion, like the lady had said, the study of fluids in motion is not as simple and accurate. The study of fluids in motion is not as simple. The study of fluids in motion is not as simple and accurate. Full stop. We can continue with that same bullet point. The main difficulty is viscosity. We know what viscosity is, not so? Yes. The main difficulty is viscosity. What does it mean? The main difficulty is viscosity. So someone is asking, what is viscosity? Who can explain it to us in the simplest terms ever? Yes, sir. What's your name? Sorry, come again. Can we just be quiet? We are learning. Yes, Clive.
Viscosity is
Resistance of flow over fluid. Okay, it's okay, but it's not really getting to the point I was looking for. Or the easiest way you can explain something to a 5-year-old. Yes, sir. What's your name? Chulu. That's your surname?
No, my first name.
Okay. Yes, sir.
So viscosity is like the ability of the fluid to flow. So if it can flow that much, that means it has like a higher viscosity. It describes how thick.
Okay. I can get something that you're trying to get to. Yes, sir.
Describe how sticky or thick the fluid is.
The latter word, thick, is a part of it. The sticky part, not really. Anybody else to add on to that? Viscosity, yes, sir.
It's a measure of fluid resistance.
Yeah. So the movement and the resistance and the ability for it to flow, that is one part. But I was looking for something that is a bit more easier to explain to someone. They say you should know something to a point where you can explain it to a 5-year-old. So for you guys that understand it, what or how can you put it? So I like his definition, though it wasn't complete, or he infused in things that are not there. But viscosity is just how thick or light a fluid is. So to marry it with your points, the resistance comes from the fact that it's thick, right? If you pour it, let's say, what are we working with? Glycerin. You know how it is. So glycerin is thick, and so we expect its viscosity to be what? To be high. And then there are things like maybe kerosene and water. They are on a lower end of viscosity. So, yeah. Okay, so let's continue. As we will be dealing with liquids, 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 comma, we will neglect compressibility of the liquid. We will neglect compressibility of the liquid. Full stop. So we continue. This is incompressible flow. This is incompressible flow. This is incompressible flow. Are we there? This is incompressible flow. And that's the assumption that we're getting, full stop. This is not a valid assumption for gases. This is not a valid assumption for gases. Okay? Classification of flow pattern. Who's got a tissue or something we can use to erase this? How did I forget you? Okay, so subunits. So classification of flow pattern. Yes, sir. Abwanje? Why are you looking at it like that? Senzo yangana mushai. Now I'm also questioning. Thank you. Okay, so let's move on. Classification of flow pattern. Okay, as a subunit. So we're interested in just the dynamics of fluids and how they flow. So we're trying to get a bit more on just the general concepts, and the terminologies. So there are different patterns of fluid flow. 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 Usually characterized by time and distance. Usually characterized by time and distance. Usually characterized by time and distance. So let's start with time. Let's define the flow of a fluid characterized by time, and then we'll come and explain it through the characterization of distance. So for time, just write time, then for colony, let's write something about that. A flow is steady if the parameters describing it. A flow is steady if the parameters describing it a flow is steady, so the steady is the steady, This word is very important at this particular stage. A flow is steady if the parameters describing it, example given, flow rate, viscosity, flow rate, velocity, pressure, etc. Example given, flow rate, viscosity, pressure, etc. And close the bracket. So I said a flow is steady if the parameters describing it, open bracket, e.g., flow rate, velocity, pressure, etc., close the bracket, do not change with time. Do not change with time. So that definition is important. It's just have it with you if you're describing something. Do not change with time, full stop. Then you continue and say, otherwise a flow is unsteady. Otherwise a flow is unsteady. Otherwise a flow is unsteady. Adam, you're not writing. Nakumbuka when I was it grade 5 or 6? Those excuses were very common. Madam, my pen is done. Please. So now the teacher would ask you, so you didn't know that you'll be having a class today? Or you can ask from your friend. So it's important to, I know this material, you have it. It's important that we go through it the way we do. So when you go back to your rooms, you go through it again one more time. By the time you're doing it for the third time, most of it has stuck. I don't know how you study, but scientifically proven, they expect you to go through a material at least 3 times for the majority of that information to stick and be with you. So you can say that us going through this is 1 time. Go back to your room, you do the 2nd time, and then even per group study you do. Okay, so let's define flow pattern in terms of a distance. You guys are part of the class, eh? Like those two just coming in. You're part of the class? Huh? Are they part of the class? College is interesting. Okay. So let's describe this pattern in terms of a distance. So I'm dictating. A flow is uniform. A flow is uniform. A flow is uniform if the parameters describing the flow do not change with distance. A flow is uniform if the parameters describing the flow do not change with distance. A flow is uniform if the parameters describing the flow do not change with distance. Full stop. We continue. In non-uniform flow, the parameters change from point to point along the flow. In non-uniform flow, the parameters change from point to point along the flow. So parameters such as the flow rate, the velocity, the pressure. I think the next time we meet to discuss further exactly how they change from one type or size of a pipe, whether you're reducing the pipe or increasing it with regards to this pattern. Okay, so let's write something next just after that. From these definitions, so the definitions of flow in terms of time and distance. So from these definitions, almost all flows will be one of, almost all flows will be one of one steady uniform flow. Second one is steady non-uniform flow. Third one is unsteady uniform fourth one is unsteady non-uniform flow. Okay, so from these definitions, there's 4 further definitions that will give more context to the flow of a fluid can be categorized. So the module has explained a bit more on what they are. Yeah. Let's get something more interesting. Fundamental equations. Fundamental equations. Fundamental equations. You're making a lot of noise. We're just here for an hour, guys. Mzaenda mshimiki. It's already 40 minutes. Okay. To develop equations describing fluid flow, to develop equations describing fluid flow, to develop equations describing fluid flow, comma, we will work from relevant fundamental physical laws. We will work from relevant fundamental physical laws. We will work from relevant fundamental physical laws. And the first one we can focus on is the law of conservation of matter. The law of conservation of matter. And this we still can remember from high school, not so? What does it say? The law of conservation of matter? Matter cannot If you've never heard of that phrase before, you do not belong here. And it's not too late for you to stop and just change direction. At least from such phrases in high school, they sort of informed you if you could be an engineer or not so. But if you've never heard of it before. Okay. So let's write this under the law of conservation of matter. Matter cannot be created nor destroyed. Matter cannot be created nor destroyed. Matter cannot be created nor destroyed, open brackets, except in a nuclear reaction. It's that bad. Yeah? Except in a nuclear reaction. Close the bracket. Close the bracket. But may be transformed by chemical reaction. But may be transformed by chemical reaction. But may be transformed by chemical reaction. Are we together? So let me just read it through. So under the law of conservation of matter, we said, matter cannot be created nor destroyed, open bracket, except in a nuclear reaction. You close the bracket. But may be transformed by chemical reaction. Okay. The other law that is very important for the development of equations going forward is the law of conservation of energy. Who remembers this one for energy? How different is it from the first? All right, so let me dictate. We see where it's different. Energy cannot be created nor destroyed. Energy cannot be created nor destroyed, comma. Energy cannot be created nor destroyed, comma. It can only be transformed from one form to another. It can only be transformed from one form to another. So identify the difference between one for matter and one for energy. So sometimes we'll ask you just to differentiate the two or the three with the one that we're going to be given now. Okay, so I said energy cannot be created nor destroyed. It can only be transformed from one form to another. And this takes you back to physics, not civics, but physics, yeah? When you put something, could be any mass on a certain elevation. At that particular point, it has got what? Potential energy, right? And then, what's the kinetic energy at that point? Zero. Then when it starts to drop, what happens to the potential? Reduces, then the kinetic. Yeah. Okay. Another fundamental law that is going to help us explain more of what we'll be doing the next time we meet. Law of conservation. Everything is the same up until we come to momentum. So the law of conservation of momentum. The law of conservation of momentum. They've replaced these tubes, right? Do we have a switch somewhere? Sasa mnafuna check kuyasha tukomboke te. Eh? Huh. This is not bad. If I didn't have an engagement at 18, but we'll still stick to the 1 hour. But this is great. This is awesome. Okay. The law of conservation of momentum. Let's get the definition. So a body, regardless of the body you have, a body is in motion. We don't just mean physical bodies, human bodies, yeah? It could be anything. It could be a car, it could be a desk, it could be a stone. So a body in motion remains in motion. A body in... Guys are talking too much at the back. At one, so the more you talk, I am forced to shout. Naturally, I don't like shouting. It's, I think it drains me more. Also, I wake out around 18 hours, so if I talk too much, then I won't lift. Which reminds me, what do you guys do after classes? Eh? You can be what? Ah. Oh, you guys are in first year, right? Well, we're talking around where we can find a space we can bring the gym, so to speak. Huh? So, and I'm mentioning this to you because, hello? I'm mentioning this to you because you and I are still together. First year, second year, third year. The third years are gone. Find time to just look around, let it make sense. I wish we had someone from the, is it Nadeso? What's that called? It's Nadeso, right? The committee, the union, yes. A place where you guys can come. But then the problem is, if we open it up to everybody, everybody will just show up at the same time. But then we've got a strategy where we can say people can show up around this time and then the lecturers can show up around a certain time. But again, look, it's, so you guys are still young. I always tell people this, like you're still young. Lifting is not so much mandatory, but if you started now young, it's very beneficial. So what happens is that as you age, when you hit 30 going down, going up, you literally start losing muscle. I was like him. Huh? I was like him. But anyway, what I can say is that it's not always that you have to go to the gym, but just find something that keeps you active. It does something to your mind. It unwinds, it keeps you active. You can easily understand what you're doing. But again, we're different people. Others, the fitness bit isn't so much, but okay, we're almost done. So I said a body, time to keep quiet now. Can we keep quiet, guys? A body in motion remains in motion unless some external force acts upon it. A body in motion remains in motion unless some external force acts upon it. A body in motion remains in motion unless some external force acts upon it. Full stop. This is Newton's second law. So the physics that we ran away from still comes back, yeah? Except where we are now, we're trying to literally apply it to solving problems. This is Newton's second law. This is Newton's second law. This is Newton's second law. First law. No, it's a second law. You've seen it somewhere as it being the first law. Yeah? What's the second one then? That's the third one, sir. You've forgotten the first one. Do your research, eh? Okay. So Newton's got 3 laws, not so? Identify which one is which. Okay. This is the interesting part now, the continuity equation. So the continuity equation is the one that gives birth to water flow in pipes. The continuity equation. Okay, so let's write something about this, just something very short. Assuming that the flow is incompressible, assuming that the flow is incompressible, assuming that the flow is incompressible, discharge in is equal to discharge out. So denoted as just a Q subscript in is equal to Q subscript out. Assuming that the flow is incompressible, discharge in is equal to discharge out. So, all right. Then you can say, but discharge is equal to area by velocity. So we can say this is 1, 1, 1. This equation, if you've never come across it, here it is. Have it like it should be part of you now. Okay, so we're going to use it a lot, not just in this course, but subsequent courses that are coming. What are the units for discharge? Cubic meters, let's say per second, right? What are the units for area? And what are the units for velocity? So these two are able to relate to each other, not so? Yeah? So this is just to prove that this equation is correct. So you can even write it somewhere so you just don't forget. But usually these are the symbols or denotions we use. Q usually is for discharge is equal to area by velocity denoted by a V. So what this means is that Okay. So what this means is that a pipe could be coming in that way, and then it just sort of reduces. So what we have here can be discharge 1, but then the pipe has reduced, then we also have a discharge 2. The dynamics here have changed. The velocity you're having, it being the entry point to the point where what is just leaving, things would have changed. So what would change? The area is changing, right? As well as that will affect the velocity, but then this will also affect pressure. We'll talk about it in the next class and topics. But then from this, you can easily say Q1 is equal to area 1, velocity 1. But then I also know that Q2 is equal to area 2, velocity 2. And then borrowing from the last statement that we wrote, which is from the continuity equation, and we said what goes into a pipe needs to be the exact value of whatever was entering, not so. So what is going in should be the one that is going out. We are safe to say in this case that Q1 is equal to Q2, and this allows us to say area 1 multiplied by velocity 1 is equal to area 2, velocity 2. This equation is very important as well. I mean, it's just related to the one that I told you to know or pay attention to. If you fully understand how this works, there is no amount of branching I'm going to bring either in a test or in a quiz that is going to be tricky for you, because everything stems from here. You just need to understand what is the area at that particular time and how can you get your velocity. And everything gets to be relatable in that sense. Yes, sir? Yeah, something like that, but we'll get there. We'll get there. 4 minutes. Okay. So something a bit more. Yes, sir.
So what changes velocity?
What changes velocity? The size of a pipe. Have you ever, now I'm sure you have done this, unless otherwise. You are watering the garden with a hose pipe, right? Yeah. So whenever you constrict, you're making the diameter smaller. What happens to the jet? Yeah. So some science like that. So this is one of the simplest typical branches you have, but then let's look at something a bit more, or with junctions. So if we have a pipe going this way, this one goes to block A, and then this one is going to block So if you're having your A1 and the velocity 1, this one will be your A2, velocity 2, A3, velocity 3, and then of course this is the direction of water and then it's leaving. So nothing happens by accident. The amount of water you're going to receive here is as a result of the diameter of the pipe that is taking the water there. So we can say from mass conservation, we can safely say discharge 1, which is the one that is just entered. So you can say Q1, Q2, Q3. So we can safely say from this law, it permits us to say Q1 is equal to Q2 plus Q3. Does that make sense? And this is us ensuring or making sure that there are no leakages at any point. So whatever gets to outflow on the other end ultimately should lead to the summation of what was the initial amount entering there. And if this is okay, then we can safely say area 1, velocity 1 is equal to area 2, velocity 2 plus area 3, velocity 3. Yeah. There's a very good example which, as you revise this work, please go through it as well. We'll come and look at it the next time we meet. Just on the next page, page 68. So there's a mass conservation problem. Just something as basic as this. It's got 2 branches. But then prior to that, there's a smaller pipe that is branching into a bigger pipe before it spreads. And then there's a table that's been given for you to fill in the blanks. That example can be solved just by understanding what's happening here. And also knowing that you guys are good mathematicians, right? So the majority of it will just be about which one do you start with that has got the most parameters. Once you solve it, it's going to allow you to solve the other one. And then just knowing how to make which one the subject of the formula. Okay, so next time we meet, so the next time we are meeting, see, the problem is I'm traveling a lot. And anytime that we haven't met, trust me, I'm not in Lusaka. But then the trips are only going to get worse. So I'd rather we get done. We push as much as possible. So, much as it's liberating for now because you're not being under pressure of there's an exam or a test coming, the truth of the matter is, my exam, if you're seeing a paper for the first time, it's tricky. You would have preferred to have seen a test. So, but again, we can't sit like this. You're not going to write anything on Thursday. I would want you guys to write something on Thursday. This Thursday. Up until where we've ended. Okay? So, through the class rep, take this as an official notification that we'll be writing on Thursday. Same time, but sir, we need a better venue. Yeah? Hoping there's no one using it around this time. Yeah, get in touch with me. If we wait, let me have your attention. Trust me, if we waited up until just the exam, you guys won't do well. Okay, so let me give you a test where you can experiment and at least get a 0 so that you can pick yourself up. All right, any questions here? Sir, just come and raise this. He's got a question, it's important. Yeah.
So does it mean beneath the pipe's diameters vary? This is the same.
No, it won't be the same. For this example, for this,
Yes, for that.
yes, the idea is that what is going in should be the same, but the major difference will be the velocity. Here, there's so much room, so water will just be flowing naturally. But the moment you constrict it, it has to rush for this equation to balance. Okay, so there's an issue where a pipe just gets reduced or it grows, or we can branch into that. So look into the example that follows up on page 68. Try to solve it. Again, individually solve, and then meet as a group to solve this thing. Okay? All right, so we'll see you on Thursday, and I'll be in touch with Mr. Robert here.